This is where we left off, right? We were talking about roulette wheel, where this is like the visualization of the idea of roulette wheel, but it's just a visualization, but it's a decent one, right? Like spin the wheel, right? And here's the fixed point. But often, like if you had like a, what's up?
Did you have that arrow in MS Paint?
I don't know. I can't remember if I did. Like it looks like something I'd have done, but, oops. Oh no, I stole it from here. See, wasn't me. I know, but it seems like something I'd do, yeah. In general, if you click on an image, it'll take you to where I stole it from. Yeah, so I didn't actually. And you know what's funny? Is like I looked at that earlier and I was like, did I add that? Looks like something I'd do, but I don't remember making this. So there you go. Anyways, for those of you that don't know, I have a beautiful track record of my fantastic art in MS Paint. Anyways, if you have a population size of whatever, one thing that you can do is instead of spinning this, like, what was I saying for population size? Like mu, was mu the population size, I think?
You said mu, but it showed lambda?
No, lambda was how many you're picking. I guess really lambda should be the right one here though, because it depends on how many you have to pick. Is have lambda be, like pick evenly spaced points and spin it once. And then based on where those things are, that's what you pick. You know, it's kind of interesting. And it does give some interesting properties. Yeah, and it tends to like empirically it gives better, a nice more diverse set of things that are selected. Where if you do regular, it'll just start to dominate with whatever's big a lot. Anyways. So when we were talking about steady state algorithms versus generational, right? Remember generational is very discrete transitions where basically you replace the whole population every time. But steady state is you replace some small amount every time, right? Lambda you replace every time. Now really, when you think about it, generational is a steady state where lambda equals n, when you really think about it, but whatever, right? But if you are doing a generational strategy, we kind of talked about this before, so we don't have to spend much time on it. If you're doing a, a steady state strategy, you pick two, let's say, you know, maybe they do, maybe they don't have genetic operators apply, or variation operators applied to them, right? Maybe, maybe not. But I have to put them back in the population. Where do they go? Who do I replace? I suppose I could have a growing population where my population size grows over time. You could do that. There's nothing wrong with that. But you know, you're going to want to have some limits or some ability for that population size to shrink over time. Because, I mean, you don't want it to have like a runaway effect, right? It'd be too big. That's no good. And you also have to remember the fact that we have like a fixed population size is actually an important feature for evolutionary computation because that fixed size is the like what they're competing for, right? Like that's part of what drives evolution. So yeah, how are we going to do this? Well, you could randomly select, which has pros and cons, I guess. It could be age-based, replace the lambda oldest, right? It ignores fitness. Maybe that's good, but it might kill off the best individual. You know, fitness-based, replace the worst, but again, this might cause too early convergence, which I'm guessing you would have assumed right away, like, well, okay. Maybe a diversity-based, replace lambda candidate solutions that are the most similar. Now this one's tricky. The idea here is if you replace those that are the most similar, then you're not going to hurt the diversity in the population, right? If I were to replace those that are most dissimilar, well now I'm hurting diversity, right? So it's kind of like the other end of the extreme. Do you see what I mean? Now how one goes about measuring how similar they are, that's tricky. Okay, in similarity-based, replace the lambda candidate solutions with the most similar fitness to the offspring, similar to diversity and easy to implement with assumptions. Those with similar fitnesses may be similar in the genotype space, but that's a pretty big assumption, right? We don't really know. But if you take that assumption, then hey, you know, you could use that. It's a pretty quick and dirty way to kind of figure it out. Again, this is not an exhaustive list. You could do whatever you want. Maybe you allow your populations to grow and then you have these like massive culling events every once in a while. But then that begs the question, how do you do that? Right? So there's all of these decisions you have to make. But like I just said about with the project, and I actually do fear I've been giving the wrong impression as we go in the class. I hope not, but if I have, I want to make sure something's clear at this stage. At the beginning of the semester, when I showed you that one figure, that's evolutionary computation. That's it. Okay? Everything I'm showing you, yeah, these are ideas that work in principle or in practice, pardon me. And they'll help you make a GA to solve problems, right? Like, yeah, absolutely. But that one figure really is evolutionary computation. As long as you're following that, you can do whatever the hell you want. Even it, like, I don't really even care how like tenuously you're following it. As long as you can give me some argument that you are following that loop, I'm very happy. It's evolutionary computation. Everyone's going to be happy. Okay? So don't think that, like, I'm giving you very concrete examples with like, oh, here's some selection things, what the variation operators are, generational, steady state. Like I'm giving you specific examples, specific algorithms, GA, the next topic's genetic programming, right? Like I'm giving you specific examples, but they should not distract you from that basic loop, okay? I want to be clear, and that loop is the fun of evolutionary computation, right? Learning about GAs, great and all, but right? If you like GA, I'm happy, right? I think they're great too, right? But it's that loop and the creativity around there where you play however you want, that's where it's most interesting. So, okay, look. Here, what do I have? Survivor. I don't know why this is a subsection. I'm not sure that should be a subsection. Survivor selection. Oh, I guess it is a form of survivor selection. We talked about elitism already, right? Where, you know, regardless of the generational steady state algorithm, elitism is commonly used in your populations. Now, that does come with a cost that we did talk about a little bit before, but to make sure the idea of elitism is clear is you pick some small number, typically, of the population that automatically gets copied to the next generation unchanged. The motivation of this is you don't want to lose track of the best thing. Because it wouldn't be, like, in a lot of GAs, for example, you could obliterate the best candidate solution through selection and variation operators, okay? So if you don't want to lose track of that, have something like elitism, okay? Now, there are other ways you could address this problem where if I never want to lose track of the best thing, I could just save it somewhere else, not in the population, and just always have track of it, keep track of it, right? But then again, if you have something good, you might want its like genes to be in the gene pool for a longer period of time. So maybe I should leave it in the population. But if I do, that might bias the population too much. I mean, this is even with talking like an elitism size of 1, okay? If you have elitism size of like 5 in a population of like 100, that's huge, right? You're going to converge really fast. It's going to really affect it. And you might only think like 5% of the population, yeah, it's going to start to dominate really quickly, especially when you were giving it like a favor, like you are just favoring it entirely, okay? The whole idea of convergence in general is even without elitism, these algorithms will converge. So even without the pressure of elitism working towards convergence, these algorithms will likely converge based strictly on fitness. So there already is a pressure to converge. By adding elitism, maybe you're going to hurt it a little bit by like biasing it too much and maybe it converges too quickly. Although it is so common to have elitism, it's important to be aware of the cost and how it can affect your search and your ultimate answers. And this is where there's kind of like, raise your hand if you've taken like another machine learning e-course, related-ish at least, okay? So I always find it interesting how there's almost like a struggle between the use of these algorithms for, like, as a computer scientist, like, I think these algorithms are interesting and I like using them and I like exploring and playing with all these things and how does it affect the results and whatnot, right? But that can be entirely in conflict with like its practical use, right? Where it's like, great, that's fantastic. What's the fastest route, right? You see what I mean? Where like, okay, you know, so elitism, it's fun to think about. In practice, people are throwing it in there. It gives them good results. They're happy, okay? But it's fun to think about these things. Yes?
Is there any cases at all where it'd be smart to keep the worst chromosome?
Why not, right? Like, there's value in that. My guess would be if you're keeping the worst one, then presumably, I'm thinking of this in the context of convergence over time. If you are constantly including lower quality ones, now there's a discussion to be had here. This is an interesting question. For those of you that don't understand the question, what if it's like you do the opposite of elitism, where maybe you are doing elitism, but you are also perhaps keeping the worst one in the population? So I'm thinking, if the population is converging, that worst one is probably going to add diversity to the population. Now, remember, be careful not to think of like diversity and effectiveness as mutually exclusive things. They really are two different dimensions. You can have things that are diverse and really good too, but the value of diversity in a population is really important. Super important. Otherwise, you converge too quickly and you won't find reasonably good solutions, which hopefully you had a chance to kind of tinker with a little bit in assignment 1, where we probably didn't put a big focus on like diversity as a measurement because it's a hard thing to measure often in general. But you could see how playing around with the algorithms and the settings, maybe they converged too quickly, maybe you changed them, it actually like took a little longer, but you got better results. You know, these things are important. Now, where this gets kind of like interesting is, okay, so you're always promoting the worst one, okay? And you're making a copy of it, let's say. And this will come down to implementation details on how exactly you implement it. But I'm thinking if I implement it the way I did, like elitism, and I just make a copy, so the next generation, everyone's available for selection. Sure, a copy gets made over of the worst one and the best one, may or may not be the best one. But if I have the worst one there, okay, great. But the worst one is now still able to be selected for crossover. Maybe. Because if we were doing tournament selection, even with the size 2 tournament, unless you picked the same chromosome twice by chance, which based on your implementation, like remember with tournament selection, you picked K. If you have a population size of, let's use what they use here, mu, right? And I pick K, where K is like 2 or 3 or something, right? And of that K, I take the best one. There, that one gets selected, right? With a K of 2, depending on how my random numbers are picking K, if I allow like pick with replacement, meaning I can pick, let's say you always put it at the index n-1 or mu-1, right? The only way that one could ever be selected for crossover or mutation or something would be if I lost my train of thought. Where was I going? Is if you pick the same one twice. Because otherwise, if you pick one and the other, this one will never get selected in tournament selection. You see what I mean? Now, other things like fitness proportional, where something like this, it could still be picked. But then that makes me think, like, well, what if I don't pick like the worst one? What if I pick like 5% of the population, I pick like 5 ones, right? Okay, that's very interesting. But am I biasing the search in some way? Selection should already be kind of like working that out, but I don't know. All this is to say, try it. See what happens. That's usually the answer with this type of stuff. It's so strictly empirical. Sometimes it works, sometimes it doesn't. Sometimes it works for you, but not them, and vice versa. It all depends. So interesting questions, fun. All right, yeah. Okay, similar. Elitism, okay, great. Now, other ways to encourage diversity. Well, you can okay, how do you encourage good fitness? Well, your fitness measure and your selection, right? How do you encourage diversity? Maybe we can have like a measure of fitness and we also select based on the diversity as well, right? You could do that, but that's a very like active form of enforcing diversity. There's nothing wrong with that. But you might remember, like in a similar way when we were talking about representations, where if there's a way to bake something into like the representation to reduce the search space, that's better than like having anything like active, like computational, doing an analysis on something, right? Remember how like with TSP, don't have an integer representation, have a permutation of integers, right? Okay, you bake it into the representation. In a similar-ish way here, there are things we could do to the structure of our algorithm, let's say, where it like implicitly will add, like passively encourages diversity, where you're not actively like doing any measurements in selection, but there's something about the algorithm structure now that kind of encourages it. That's interesting and that's good. So I'm just going to show you two very simple ideas. And the point of these ideas is hopefully you get a sense of like I've been saying for over a month, try whatever the hell you want. These next two ideas, I hope it gives you a sense of like, yeah, that's weird. I guess it could work. Like to get a sense of like how trying these things might work well. Okay, okay, why is diversity important? Okay, diversity is how much a member of the population is different from one another. Diversity is important within the population. It balances exploration versus exploitation, and it prevents premature convergence, which is never good. Or it's often not good. As with anything with evolution computation, there's no rules on how you do it. Do whatever you want. You can explicitly add diversity measures, like I was saying, maybe bake it into fitness calculation or something. Maybe you only have similar individuals compete with one another. Or you can like do something where, like this, for example. What if you didn't evolve one population? You just didn't. What if you evolved multiple, in this example, 3 separate populations? You let them evolve independently from one another. Basically, each one of these in parallel, doesn't really matter if it's parallel or not, will like do their selection variation operators. So they will all have a chance to evolve independently from one another. Now, think about, like let's say after 1,000 generations, what do you expect these populations to look like? Are they going to look the same? Maybe. Are they going to look different? Maybe. The point is, there's probably going to be some like speciation, for example. As like a fancy word to use, but like differentness there. And then, every once in a while though, you allow for migrations, where maybe a bird flies to that island or something, and is able to like reproduce with the ones here. Now, how you do this, you have to be careful, because it's easy to implement poorly. Because the problem is, if the number of migration, in my opinion, if you go in the literature and conferences where people are talking about it, they always allow for like a small number of things to migrate. But the problem is, if you already have a population that's converged, and you add 3 things that are very different, they're going to get stomped out quickly. So you need to have like a critical mass of migration in order for this to like really happen. The way I always implemented it, and everyone hated me for it, but I think it worked really well, was after 1,000 generations, you combine all of them, shuffle them, split them up again. Entirely, just there. God came and combined them on one island and shook them, and there, done, right? There you go. That's how it happened. That way, they're not going to get stomped out too quickly, right? So this is an example of like, wow. Like, and by the way, do you see what I mean of like, oh, I was talking about like, try different representations, try different genetic operators. Who would have thought like, evolve 3 separate populations, right? But that's the point. Think outside the box. Try it. Here's another one. What if you treat your population like a circle? And by the way, like this is like modeled after like things that happen in reality. And the example I always hear is like these like little lizards living around mountains, right? I think it's in South. Honestly, this might be an apocryphal story. I don't know, but the story is like lizards around mountains in South America or something. These big mountains, where over centuries or millennia or however long, very long periods of time, you'll have these things that are like the same species, but as you get further and further away, it becomes more and more difficult for them to reproduce with one another. So the idea here is, okay, when you select one, and then you pick another one for like crossover, for example, it has to be within some amount. And then you get this like interesting, I shouldn't call it continuous because clearly there's a discreteness to it, right? But you kind of get this like continuous, for lack of a better term, of diversity kind of like happening within the population, where it's almost like there's like a topological thing going on there, which is pretty neat. Again, by just messing with how we're thinking about the populations, maybe we can actually do something interesting there. Here, I think in this example, this was taken from something I made a couple years back where I said you can only pick between here and here. But of course, it could be like probabilistic, right? Where you're likely to pick something here and less likely the further away you go, right? That's probably better, but whatever is easier to implement doesn't really matter so much. Any questions about these ideas? Cool. Hopefully you kind of get a sense too that like, if you were to think, okay, how do I implement that? None of these ideas should, at this stage, scare you in terms of implementation, though, right? Like, oh, okay, I guess I could implement it. All of these things are still relatively simple. Yeah, that doesn't necessarily mean trivial, but like straightforward, simple. All right, so at the end of the day, and I've been talking about diversity and how it's like difficult to measure. It really is difficult to measure because, well, there might be multiple things that we could measure, but what's the right, like, I don't really know. There's like, for example, should we measure diversity in the genotype space, like in the encoding space, like what the chromosomes look like? How similar are those chromosomes? And, well, this is going to depend on the encoding, right? Like you could have something like Hamming distance, like we talked about, right? Or Levenshtein distance, which is similar-ish. Or like if you had like two Hamiltonian cycles, how could you compare their genotypes for like similarity or differences, right? Like, is there a way I can quantify that, right? So that's kind of interesting. Or maybe you should really like compare them like in the phenotype space, right? So like maybe their encodings are wildly different, but what they mean in the problem space are very similar, or vice versa, right? So maybe, yeah, it could be very different. And then like algorithm space, well here, we would kind of like bake in like, well, distance is going to be like an easy way to measure diversity. If you built it into there, the bigger the distance around that circle, right? Or the more islands, you know, you can start to see how that would affect it. Any questions about this? There are, a number of years ago, and I may have already complained about this to you. It's one of the best books ever. Why Greatness Cannot Be Planned. I lent it to someone, and it was never returned, and I don't remember who I lent it to, and I have a bad habit of doing that. But that book is it's really good. And like the whole thing is like, they were doing like novelty search. Let me do a quick thing here. No. See if we can find some like images. No, they're way too technical. Well, novelty search. Its whole thing was like not focused on fitness, but on differentness, like measures of diversity, and how you want to encourage your search to be looking for like novelty. And you were able to get like things that you would never otherwise be able to get by virtue of like the search space and the problems being solved. But that's another thing. Okay, any questions at all up until this point before we start talking about genetic programming? Okay, because everything up until now has been very genetic algorithm focused, okay? Now, the representations, the variation operators and whatnot. A lot of these are still applicable to a variety of different forms of evolutionary computation, genetic programming included. In fact, you will kind of see that genetic programming really is just a GA. But genetic programming really is our first different algorithm we talk about, but again, it's the same, but different enough. So with genetic programming, it's basically just a GA specialized for evolving functions or programs or whatever you want to call them. The genotype, traditionally speaking, is a tree structure. We talked about it before, those S expressions. And the genetic operators that work on the tree are going to be used. Remember how we talked about the operators and operands, the leaves of the trees and whatnot. But at the end of the day, ultimately, it really is just a GA specifically designed to evolve these tree structures. You don't have to have a tree structure for genetic programming. There's other types. There's linear genetic programming, graph-based genetic programming, acyclic graph. There's a lot of different ones, but traditionally the tree is your basic one to start with. It's fine. So, raise your hand if you've done machine learning before, right? Okay, great. So, machine learning. Why are we doing machine learning? Well, if I were to say build a classifier to test whether or not someone has breast cancer based on these values, and I say write that program, I'm going to be in big trouble, right? I'm going to look at this table of data and be like, if fitness is less than 6, and the sum of these is less than 6, it's benign, and then I'll tell you, it's going to be a ridiculous process of hypothesis, check, yes or no, and whatnot. If I'm handcrafting a classifying function for something like this, I'm screwed, right? Especially because this is probably going to be lots of lines long, right? I don't want to go and start writing a bunch of if statements to do these comparisons to decide what's it going to be. So this is where genetic programming comes in, or genetic programming, yes, but this is where machine learning comes in. Or really we could say the first step is statistics, right? Maybe even before statistics you might just do some very basic data visualization or something. See if you can find some obvious trends where you could just draw a line and you're all set. Unfortunately, this is a higher dimensional space, so it's kind of difficult to do that, but maybe you could start to distill these trends, right? You could really start to do your data science, where you're just tinkering with the data, trying to find trends, seeing what you can do. Maybe you start to do some very simple statistics, you start doing something like logics, you do some regression analysis, I don't know, but you're trying to figure out, well, how is this going, And then you decide, no, let's just use machine learning, right? Just give an algorithm, be like, here, just tell me, build me a good classifier, and it gives it back to you. Huzzah, right? Genetic programming, so first of all, it's kind of funny. It's hard to put your finger on what exactly evolutionary computation is. Is it machine learning? Well, it can be. Is it AI? It can be. Is it optimization? Yeah, it can be. Right? So it's a big thing that has multiple different uses, and genetic programming, a classic use of it would be machine learning. So what if I wanted to use genetic programming to do machine learning? I want to build a classifier for something that looks like this. By the way, here's a bit of a spoiler. Why would you want to use genetic programming for something like this? Like I said before, if I could use something like k-nearest neighbors, use it, okay? But let's say it's really difficult. Maybe I could use a neural network. It's going to be great, right? But why use genetic programming? Well, the one really amazing thing about genetic programming is at the end of the day, you get functions that you can look at and you can think about and understand. Where if you're doing something like a neural network, well, you got a black box, good luck. And I don't care what anyone says, you ain't figuring out what the hell it's doing, right? So there's a huge value, especially in the world of explainableness, which becomes very important in fields like healthcare, for example. If you have a neural network that says this person needs neurosurgery right now, and I take it to a neurosurgeon, and I say, well, this person needs neurosurgery right now. And the neurosurgeon goes, why? And I say, well, because my algorithm said so, and it's right 99.999% of the time. And they go, but why? And I go, I don't know, right? That's going to be a problem. They're going to be like, okay, no, I need to know why. So, explainable AI is an important thing. It was a really big buzzword a few years ago. It still is, but I feel like it's not as important. It's not as buzzy as it used to be because everyone just kind of like gave up. Anyways. So, I think I spoiled this a bit. The goal is to build a classifier to determine if a patient has breast cancer based on the observation. So what should it be? If size is greater than 4 and shape is 3 or shape is 5, then it's malignant. Otherwise, it's benign. Or if the thickness is greater than 4 and thickness is less than 9 and malignant, then malignant, else benign. Like, we could play this game forever, but who wants to go and sit down and look at thousands of rows of data and do that? No one. That's insane. We have better tools for that. If you could plot the data and be like, oh my gosh, all the numbers greater than 0 are positive and all the numbers less than 0 are negative, right? Like, wonderful, good for you. You've got a classifier, you're all set, easy peasy, right? But in general, real data, you're screwed. So, yeah, it would take very careful understanding and an immense amount of understanding of the problem area. How many of you in here are neurosurgeons? How many of you in here are experts on breast cancer? Right? Like, good luck. So, however, AI and machine learning are often used to automate this process. And like AI and machine learning is going to try to like generalize anything it finds. Now, look, obviously, when you're doing machine learning, you want to get like 100% accuracy all the time, right? Obviously, that's ideal. In practice, though, by the way, set your expectations accordingly. That's usually not going to work, right? The real data is often, there's so many outliers. Maybe there's issues with how the data was collected. There's bias in the data. Maybe there were just errors in the recording of the data. And just everyone's different, right? So good luck. Good luck. By all means, if you could find something that's perfectly able to classify, that's wonderful, but just set your expectations accordingly. Okay. So if we're putting our evolutionary computation hats on, your general evolutionary computation strategies aren't really well designed for something like a machine learning thing like this. But genetic programming is. With the use of a clever representation and genetic operators designed for this representation, we can now actually build an evolutionary algorithm that is evolving functions or programs, whatever you want to say, classifier programs to correctly classify this data. Fitness could be something as simple as how accurate was it, right? If one classifier is 90% accurate and the other one is 97% accurate, good, right? So there we go. But how are we going to do this? Well, S expressions, symbolic expressions. We can encode our programs or our functions as these trees. And I showed this figure before, right? This would be like 1.2 minus x times y, right? That's just a mathematical expression. Is your hand up or are you just sitting? You're just sitting. And then the length is less than 5.2 or it's not red, right? That means something. And here's one. This one's crazy because it's got 3, right? Because it's got if. And what's kind of neat about this one is, and this one as well, you'll notice like here, for example, everything like presumably x and y are going to be like numbers, okay? So everything in here is a number, where here we're mixing numbers and like Booleans, which is kind of interesting. And similarly here, right? Well, I guess that's like an instruction. I don't know. But anyways, the point is, here is an easy way to encode programs or functions, whatever you want to call them. A mathematical function is a program as far as we're concerned here, right? So consider the above program function for the breast cancer identification problem. If size is greater than 4 and shape is 3, blah, 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 okay. If true, in this particular example, what we'll do is, if this evaluates to true, it means malignant, let's say. And if this expression evaluates to false, we'll say it's benign. How about that? Okay, that's the idea here. So yeah, I've got this like then else. So we kind of like simplified it immediately by just like, okay, it's just going to be true or false. Okay, so this is what it is. And we can create this like this. There is an S expression that can represent that program, that expression. Right? If size is greater than 4 and shape is 3 or shape is 5. Okay? The hierarchy is important here. And you have to be aware, like, well, this is an operator that acts on two numbers, and it returns a Boolean. Okay? That means these better be numbers, and if it's returning a Boolean, whatever's up here better expect a Boolean. So the typeness of this data is going to be important. A word we use then, because you look at this, and you're like, okay, great. Okay, these are the operators. We have greater than, and, or, equality. What operators do we allow? Should we allow addition in here? Should we allow exponents? What types of like constants should we include, right? Like, what variables are there? Well, the variables are probably going to be dictated by like whatever your problem is, right? Like, these would be like the variables, right? So for like, if the expression was like size, well, this one's size is 10, right? You see what I mean? These are all like instances, right? Do you see what I mean? But the point is, how do you decide what is and is not allowed in these trees? Well, that's where the language comes in. It's the set of available operators and operands used for creating and modifying these tree structures. This is called the language. And picking the right language is non-trivial. It's not too bad, but it's not trivial. The operators and operands are something that can be adjusted as needed. With the breast cancer example, the language could be a collection of arithmetic and Boolean operators and operands. So, for example, operators could be these binary operators: plus, minus, multiplication, divide, greater than, or sorry, less than, greater than, equal, and or. Cool. Why? I picked them. Now, really, thinking about this problem, like, I'm not an expert in this data set. I have a feeling shape is probably categorical, right? Like, is there really an orderedness to the shape? Maybe there is. I don't really know. But my guess is that's probably like category 1, category 4 or something, based on something. So does it make sense to like multiply the thickness by the shape? No, right? So maybe including something like multiply doesn't work. But then again, like maybe thickness times size kind of makes sense. I don't know. It's kind of hard to say. But the point is, you have to be intentional about what your language is. And you can invent your own operators for the language as well. All right. And some unary operators, sure, sine, cos, e, naught, why not, right? Now again, I don't really know what like the cosine of the thickness is going to give me, but maybe it's important. I don't know. Maybe it really is important because it's good, something cyclical. I don't know, right? But there we go. E, I don't know. E to the power of mitosis. I don't know what that would mean. Maybe it matters. I don't know. This is where some familiarity of the data might be helpful in picking what the language should be. And what operands? Well, some constants like for, true, false, like literal values, right? Maybe constants isn't the right thing, like it's just some literal value. And variables. The variables would be things like size and shape, okay? So maybe this right here is something. I got x and y, maybe those are a stand-in for something, I don't know. When working with mathematical expressions, the language could be just mathematical operators like numerical operators, like here, right? So this is showing you, here's one where there's no Booleans, for example, which is kind of nice because then you don't need to worry about types. This is like singly typed. People call this untyped, which is weird because it is still typed. It's just all the same type. And then there's typed GP, which is when you have more than one type. It's weird wording, I agree. But this one's kind of nice, so you don't need to do any checks of like, is this returning the right type for the above operator? Do you see what I mean? Right? If this was like and up there, and this is returning like whatever the result of 1.2 minus x is, that's like meaningless. That's a nonsense, inadmissible statement. Yeah. Okay. Oh, typed versus untyped. Okay, yeah, great. Any questions at this stage? Yes?
So you have those sort of categories as unary and binary.
Yeah.
So like when we're building our language, are we choosing like one of those groups or like very specific operators?
You would pick specific operators. And like it's important if it's like binary or unary because that kind of helps the system know like this tree structure, like sign, should only have one child, right? If it's binary, it should have two. Not to be confused with Boolean, right? If you're like, well, not as a Boolean operator. Yes, it is, but I'm talking about binary versus unary, how many like operands it needs. So just be careful. And again, I really want to emphasize here that like, oh, like I don't get the variables. Consider that this is like, imagine we're building like f of, I don't know, t, size, shape, bn, and mitosis. Yeah. Like consider like I'm building a function on these things. So for any instance, I would plug in whatever these values are, right? For any instance, the ID number is obviously, hopefully clear. Like you're not going to divide that by, it's just an ID. It would be a function of these for every instance, right? So when I say like, oh, like if you go down here, you would plug in, okay, to evaluate this particular instance, what is x and what is y? And then you would do the number crunch. You see? So we're building a function on these things. Yeah, leave that there for now. Cool. Typed versus untyped. Okay, notice that the mathematical expressions only had numerical values. That's nice and easy. However, the breast cancer example, we're mixing types. We have Booleans and numerical stuff. So there will be some overhead that needs to be taken care of to deal with this. Now, look. Before I carry on, I should have said this before. I'm not going to ask you to build genetic programming system from scratch. You're not going to do that. It's too much. It's hairy. You're going to use a package that is kind of, it's great. It's great, but it could be like improved. It could be updated a little bit. It's a great package. It's called Deep. It's really popular. And you're going to use that as like a genetic programming system. It's going to make your life a lot easier. So when you're thinking like, oh, type, now I'm going to need to check how many, no, the system will kind of take care of a lot of that stuff for you, so don't worry too much. All right, so back to the typed, untyped. When using a language with only one type, untyped, when more than one is called typed. And generating an expression that applies an operator to the wrong type would obviously be a problem. Like shape is equal to 4 plus 7 is obviously a ridiculous statement. Because true, I mean the computer would probably be like, it's 8, right? But it's really not what we intended. Assuming this is true, right? True plus 7 is 8, everyone knows that. But of course, nonsense for our needs. With untyped, it's not going to be a problem. Fortunately, most modern genetic programming systems are going to deal with this complexity for us, which is really nice. Back in my day, though, they made us implement it. Lucky for you, you've got it good. Any questions about that? Is it just that it's so obvious that you're following along? There's no questions? Everyone's happy? Good. I'm glad it's obvious. Good. So I think genetic programming is really fun. A typical genetic programming setup: initialize the population, evaluate, selection, genetic operators, termination. Oh my gosh, it's the same as everything. The key difference is really just around the representation and the genetic operators for that representation. So we could have a very valid argument about like, is it even really, like it really is just a GA. You're absolutely right. It really is, but it's significant enough of like a specialization that people have named it. But really it is just a GA. Now, there are some interesting quirks that you will find with genetic programming in that often they have massive populations, not a lot of generations. They're very slow, they're cumbersome, and they also, because of the large populations, will have some funny selection strategies sometimes, but for what we're going to do, though, even with like on the assignment and whatnot, you don't actually need to worry about massive populations and everything. It's all going to work just fine within its system. So you could think even like you put your GA hats back on, you'll be fine. So yeah, like we talked about the S expressions. If I click this, okay, yeah. How could we do some like something like crossover? Pick two subtrees, swap, right? So if I were to copy that, put this there and put that there, what do we end up with? That, okay? If this is typed, though, you got to be careful because you can't just pick a subtree and another subtree. You need to pick a subtree, and this goes, oh, this one is going to return a number. I need to pick a subtree and the other one that also returns a number. I can't do crossover with something that expects a Boolean. So there's some added complexity there. And then mutation is, I don't know, pick a subtree and generate a new subtree to replace it. Here, this new subtree is just some root node, y, whatever. But you would just randomly generate it. Often you're going to randomly generate it the same way that you would randomly generate your population to begin with. Oh yeah, another thing too. Yeah, typically mutation is going to be lower than what you're used to in GAs. But again, this is all just kind of like basic ideas. Do whatever works. Yeah, ultimately, do whatever value works. And you're good to go. Any other questions? So we are not going to have time to start the next thing because the next thing is interesting. It's bloat. It's this interesting phenomenon that happens to genetic programming as time goes on. And we'll pick up here on Wednesday.